So with this, I would like to invite our next speaker. That is Sebastian Cammerer. He's a senior researcher, scientist at NVIDIA, Germany, maintainer and code developer of the Siona open source link level simulator. Let me present your slides.
All right, thanks for the nice words. Yeah, I think we've heard a couple of times today already about agentic AI. We've heard about Jakob Heude's talk in the panel already, and this is aligned with the talk. He's one of my colleagues. And in the next 20 minutes, I want to convince you that agentic AI is a fundamental change how we write software in the future, or even today. And yeah, since we are all now 10x engineers, let's not waste time. I have 10 times more slides, so we'll present all of them in the next minutes. If we look back in history, I think we can say that research has always evolved, and can even go back 200 years and it looked totally different. So I asked, this case was, I think, ChatGPT to visualize this, and I got this nice drawing. And if you think about it, I don't know when you started and when you joined the wireless research world, but probably the world has looked different compared to today, and I think it will also change in the future. And then we are now at a fundamental change that we will not write software by hand. Most likely we will prompt it, we will have agents, we will orchestrate these agents, and we will still do research. It's just we will use different tools, we will use different platforms, and we may be more efficient when doing research, but it's still wireless research, of course, what we are doing. Now, one example where what convinced me that there's really something a fundamental change in software was when we did the migration from Siona 1.0 to 2.0, which was essentially migration from TensorFlow to PyTorch. So Siona is an open source library. It was written in TensorFlow originally, and then TensorFlow became more and more outdated, so we wanted to migrate to PyTorch. And the estimate was this takes roughly 18 per month because it's a huge library and you need to test and yeah, all the mathematical details and so on. It just takes a while to do all of that. And then it was the time when Jakob started to look into these agentic tools like automation of translation, and it actually took him 1 month to translate the whole library from TensorFlow to PyTorch. There was a bit of manual work required, and also like fine-tuning and proofreading, of course, but still it's a fundamental change from 18 to 1 month in terms of the human invest that you do, and also the token cost was actually almost nothing. It was like $2,000 at that time, and I think today it's probably even cheaper. And that's, by the way, it's open source, so you can check the code, you can check the quality of the code, you can check the documentation. All this was done by an agentic tool, so it's something that we use in production. But also we can do other experiments. So in this case here we have an example where we take 3GPP specifications, translate them to any language that you want. In this case it's CUDA. So we took the channel models, the 38.901 channel models. We took the docx files, put it into Cloud Code. It was done already a couple of months ago, so we had Opus 4.6. It was running for 48 hours, spent like $1,500 in tokens, and the output was actually a calibrated Python and CUDA code of these channel models. And if you have ever tried to implement these 3GPP channel models, you know how hard it is to read the specs, to implement it, to calibrate it, write unit tests, go back, debug your code, and so on. So that takes you many weeks or maybe even multiple months. And then accelerating the code and so on is also a different challenge. So this is a good example that we can even take 3GPP specs and translate it into any language that we want. There's a bit of a pitfall here. So I would say the standard is not really machine friendly, so it's hard to read it. There are nested tables. Sometimes their equations are embedded as images, so it's hard to parse them. I would even say it's sometimes not even human friendly to read it, or very often. So one could probably also improve the way how we do the standards now, so make it agent ready. But in general, it shows you that there's a lot of potential behind these agentic systems. Can this also be done for other parts of the standard? Can we write a full stack? And I have one example towards the end. It's a toy example, but I think there's really a a huge potential behind it. And then another example for those of you who are following the 3GPP standardization, of course you can also have an agentic 3GPP back office. There are now many proposals for 6G. So we took one of the LDPC base graph 3 proposals. There are many proposals now, and let's say you want to benchmark them, then you need to implement them in your own pipeline, with your own decoder and so on. So the exact same implementation of the decoder, and then you implemented different base graphs from different companies, and you can compare them. So I did that here for one specific report. I took the docx file, so this is public domain knowledge, you can just download it. And I reproduced it using codecs here with GPT 5.5, so it was quite a recent result. And if you look at the reported block error rates compared to what we get out of the agentic pipeline, it's very, very similar. There's one mismatch. I actually got these results last week. So there's an 0.1 degradation for one specific rate. I need to check what's wrong here, but the rest looks very, very accurate. There's a small, you can note that there's a small shift, but this is a decoder-specific thing, so each company has a slightly different LPC decoder, so that the implementation of the decoder is not standardized. That's super nice. And then you can also do the complexity analysis as described in the standard. So there's in the run work group, there's a definition how you measure complexity of these base graphs, and you want to compare that. And I could actually exactly reproduce these complexity measures. And this is not so simple to do that, so it would have taken me a couple of days probably to implement that and run it for different codes and so on. And this matches exactly, so the dashed line and the solid line, you cannot even see the dashed line because it's perfect reproduction. I find that quite impressive, and yeah, I think many companies who have these big 3GPP back offices shows also a lot of potential, and you can, of course, also benchmark more different proposals and so on. All right, then the problem is always for these experiments that I've shown before that there's a human in the loop at a certain point. So you prompt something, you run it, you go back and you prompt it again, you refine it and so on. So can we get the human out of the loop to get even better results or faster results? And that led somehow to the AI telco engineer. So this is one open source project that we did. So the idea is a very abstract definition of this. Now we take a task description, optimized link adaptation algorithm. We need an evaluation tool, or can also prompt that, of course, a way how we evaluate our algorithm. Like we simulate it in Shona, we have some trajectories, and we want to maximize the spectral efficiency or something like that. And then we run this agentic telco AI engineer, and the output is a set of algorithms, essentially. So we get a couple of proposals, we refine it, and it's a kind of a genetic function search. That's the idea, the general idea. So can we also get creativity into these systems and find some new, because when you want to do research, you don't want to just implement a standard, you also want to find new algorithms, you want to improve something. And that's the basic idea or motivation for the AI engineer. Now a bit more, maybe, by the way, these arrows somehow when I export from my MacBook and load it on the Windows machine, the arrow size seems to be broken here, so yeah, anyhow. I think you can still read it. So the idea is that we have an orchestrator which gets the task description, and then we have multiple parallel workers or agents that implement the same task. It's a bit like some companies do that, so you have multiple teams and they work on the same task, and then at the end of the day you compare the results. And here it's the same thing, and then you can also run, you can spawn multiple ideas. So one group looks into a specific subset of algorithms, another group looks into a different subset of algorithms, and so on. And then you refine these subsets of algorithms, and at a certain point you combine them, you do genetic optimization, so you kind of kill a couple of candidates, you discard them, and you kind of focus on a specific subset of candidates, which is the most promising one usually, and so on. So there are different ways how you do this combination. So you have multiple workers that runs in an endless loop, essentially, or until you declare some objective function that is that stops, essentially, and then you get the output is actually an optimized code or proposal for a specific algorithm. From an infrastructure side, it runs into a container, so we need to run code. Of course, we need to edit the file system. We have access to the Shona documentation, so it's built around Shona. So we use Shona for like the link level simulation and for ray tracing, channel simulation, and so on, depending on the task. And of course, we need also an evaluation function to get kind of the performance, the fitness of a specific candidate. All right. That works very well, and I have an example integrated in OAI in a couple of slides. But let's first of all, this is an OAI workshop, so how can we now get hardware in the loop? How can we go one step further? This was all done in Shona, this is Python, simulated, and so on. So can we do that in a real system? This is essentially the idea or the ultimate goal. And last year, I presented the Shona Research Kit, was at Ericsson last summer workshop, the OAI workshop. So what we do is we run OpenAirInterface on our embedded platform, so in this case on a DGX Spark, connect the USRP, and then we have a real-time test bed. We can run AI workloads. We have examples how you can run a neural receiver on the DGX Spark in real time, connecting a commercial modem. We have channel emulation, I have an example there, and everything we do here is open source, so we build on top of OpenAirInterface. We make it as affordable as possible, so all the design decisions are to make things affordable for researchers, so that's why we use the USRPs, software-defined radios have the maximum flexibility, and so on. And everything comes together with tutorials, so it's documented, and should be also an important aspect is also teaching, education, making it accessible for young researchers and students, of course. Why do we need hardware in the loop? And we have, of course, great stochastic channel models, right? So we have these 3GPP models, but also Gaussian, AWGN channel models, and so on. And it's very cheap to get a huge amount of data. So can simulate thermal noise in microseconds, nanoseconds. But the problem is that, of course, it's one specific channel, it's a Gaussian channel, and there's not that much diversity, it does not really capture the reality, so there's also a sim-to-real gap in that sense. We can then go one step further or get more realistic channel conditions by using ray tracing. This is Shona RT as an example. But the problem is also there's a mismatch between reality. We don't have the real RF impairments. It's again an idealized ray tracing environment, of course. So the next step would be going to a test bed. So this is a test bed at ETH Zurich. Looks very clean here, but it's all static. So nothing is moving in this test bed. I mean, you can do some tweaks to get a bit of movement in this anechoic chamber, but it's still not realistic. And then, of course, you can go to, let's say, real-world environments. So you do real outdoor tests and measurements and campaigns, but it becomes very, very expensive to do that. And if you want a diverse data set from very different locations, different cities, different mobility scenarios, and so on, it's extremely expensive. You need to go to different cities, you need to walk around, you need users moving and all that. You need ground truth labels also for training if you want to do kind of AI-run experiments. So we wanted to have something in between, like the best of all worlds. And for that, we kind of implemented what we call a real-time channel emulator. So the idea is we take the Shona Research Kit, so the OpenAirInterface stack. We take the digital baseband IQ samples, and before feeding them to the OAI physical layer stack, we apply channel emulation. So we take the Shona ray tracer, it runs in real time on the same system. We stream the IQ samples, the channel impulse responses, sorry, and then do the channel convolution in real time with the received IQ samples. And if we do that in real time, then OpenAirInterface doesn't even know that we do this, that we have this channel emulation running underneath the software stack. It's just a way to emulate the channel here. And this gives us the flexibility to use the ray tracer to simulate different scenarios, different user speeds, replay the same scenario again and again, change the user mobility, whatever we want to do, add more users and so on, and also get the real-time aspects and the real RF impairments from the real USRP or whatever you have connected here, so the software-defined radio. And this is something that we have integrated in the Shona Research Kit, and is also part of this open source library. Yeah. And then we are running, of course, the full OpenAirInterface stack, so the physical layer and above. We've put all that in a nice box. This was a demo at GTC last year. It was nice to have a network in a box. It was kind of a nice slogan. Yeah, I don't want to go too much into detail. So this was the real-time ray tracer running in real time. The user was walking around the convention center in Washington here in the simulated environment. We had a real Quectel modem connected. It was cabled setup because this was, of course, we're not allowed to radiate in the exhibition hall, and then we stream the IQ samples to the DGX Spark, where we run the real-time, the channel convolution, so the channel emulation, essentially. And we have an X app showing us the MCS and the block error rate of the system, all running in real time. Now, putting things together, we took now the telco AI engineer, so the agentic optimizer, and we optimized, our task was to write a new link adaptation algorithm. So very simple. Was a bit longer, but essentially just optimize the spectral efficiency, so maximize the spectral efficiency of a link. And the outcome was actually quite good in the simulation. And now the question was, can we integrate it in our Shona Research Kit? So can we also use agentic tools to kind of write the C code and just replace the link adaptation algorithm that exists in OpenAirInterface today and just implement our agentic link adaptation? Don't know how you call it. So in the experiments in Python, we saw 3.4% higher spectral efficiency for a specific environment. So we took the Python code, at that time it was still Python code, and translated it to C code, integrated it in the OpenAirInterface stack, and then it didn't work. So let me see, here's the video. So this is actually with a real Quectel modem connected to it. We get the MCS scheme and you see a lot of spikes. So there was a mismatch somehow between what we had in our model and yeah, because in the simulation it was super nice. It was a very smooth curve. Everything was running super nicely. But these spikes, they were actually a bit of a problem. So we asked Cursor again to kind of fix this problem, analyze the problem and fix it. And then after a while, it actually found out that some averaging, some filters were actually too short, because in the simulation it was always just a couple of samples that we had in this in the optimizer. But in the real world, you get thousands of slots actually per second, and then it accumulates and so on. And there was essentially a kind of a buffer or window overflow, however you call it. So it actually proposed a fix. So the history of NUX was 64 observations or so, or below 64. And then it actually fixed that, and you see a very smooth curve by kind of learning from the real world and fixing that. So what is the lessons learned here? So this is now an agentic link adaptation. I don't know exactly how it works, but you can read the code, of course. No, but it's now running in the real system. So what we have learned here is that you cannot just do this, you cannot just optimize in simulations. You have a sim to real gap, and you need to do multiple, let's say, stages before you deploy a system. So first of all, you do, of course, algorithmic evolution. You can do that in simulations, do link level simulations, and so on. Then you go to the full stack, but you also need to go back. You need to kind of learn from the full stack integration, refine your algorithm, give the agents a chance to refine it, the same as what we do as engineers, what we did in the past as well, get feedback, refine it, come up with a new proposal, and then continue with that stage here. And then we can even go to the real world where we get the real network performance, and we can also optimize for that. So I don't know how much time I have. Okay, if I have 2 minutes, I have, it's just an outlook here. So what would be possible now with unlimited tokens? So this is all, let's say, simple toy cases, but now imagine we would have an infinite amount of tokens. So I had a small project, I called it NanoRun. So the idea was I took a Spark, I combined it with a USRP and a Quectel modem, and then another USRP to monitor the RF. And I asked so the task was, the prompt was to rewrite the full stack. Just connect the Quectel modem, just from greenfield implementation, and try to get a ping through it, and then do an iPerf, like get some traffic over the 5G link. And actually was running for a very long time. always debugging, and was sometimes at a certain point was even frustrated. I can't do this, and then I told him, hey, you can do it, and so on. It was a bit like working with a student, actually. I had a depressed agent, and it was actually quite expensive experiment. But then after a while, so after a couple of weeks, actually, I got a nice project, a lot of Python code, because that was part of the prompt. And yeah, this is the first ping, I think the first fully agentic ping with real Quector modem connected. The latency is horrible. It works in, I don't know, 1 out of 10 trials or so, but it works. There's a ping over an agentic stack. It's super cool, and I mean, if you think about it, then where's the limit? So if you spend even more tokens, I don't know, 10 times, 100 times more tokens, I don't know where the limit is, to be honest. But I think there's a lot that can be discovered and a lot that can be done with these agentic tools. So that brings me to the end. I think there's no way back, as Tommaso said, so we are really in the agentic age, and yeah, I'm happy to be here and discuss that with you.
Thank you so much, Sebastian. I mean, are there any questions for Sebastian? Yeah.
I can tell you where the limit is, 0 seconds.
Sure.
My question is that how do you make this whole implementation more secure? So, for example, it doesn't harm the system, these agentic AIs.
Okay, so in this case, this is research exploration mode, so it's running on a Spark that is isolated. There is nothing else running on it, so it's not secure at all. So there are no guardrails at the moment. That would be the next step, of course, to look into also how do you test all that and how do you guarantee a certain performance and so on. So this is all, let's say, open for research. So this is to show the potential. And talking about NanoRun, I mean.
And did you done any experience or any research that how you can make it more secure or not?
I mean, you can look at what is done in agentic AI in general, and I think it's not. I don't see a fundamental difference between, let's say, wireless communications and many other fields where you have these automatic software pipelines, and you can probably learn a lot from there. I think it's the same as, at the end of the day, same as if you have an engineer writing the code, you also need a certain audit and tests, and of course all this is required also if you have human engineers and
exactly.
with different teams working on software and so on. But yeah, maybe that's one important aspect that I have learned or my view in the last few weeks, months. If you think about what is the value now of OpenAirInterface or any other open source tool, the tokens become cheaper and cheaper. So the value of software is essentially the value of the tokens that you need to reproduce it at a certain point. But there's another aspect. There's also trust. And I think these open source tools, if they are used by many users, like OpenAirInterface is used since, I don't know, 10 years by hundreds of people, and it gives you a certain trust that what is in the OpenAirInterface repository is somehow correct. I mean, there may be some issues, of course, but it's somehow tested by a huge number of users, and that can be also the value now, the future value of software is that you have an open source repository, you have users, you get feedback, you get trust, and that may be the path for the future, essentially, why you open source also software at a certain point.
All right, thank you.
Thank you so much. Thank you so much, Sebastian.